In this video, we're going to talk about fluid pressure and force, and eventually use integrals to calculate the fluid force on various objects. So let's start with a little bit of a definition. If a force of magnitude F is applied to a surface of area A, then we define the pressure P exerted by the force on the surface to be P equals F over A. So pressure equals force divided by the surface's area. And let's just do an example using that. And as you can see, this particular definition does not use any calculus. So this example should be pretty straightforward. So example. Let's suppose the back of a swimmer's hand has a surface area of 8.4 times 10 to the negative third square meters. And let's suppose the pressure acting on it is 5.1 times 10 to the fourth pascals. Now let's find the force that acts on the swimmer's hand. So we're going to use that formula that we had, the pressure equals force divided by area, and then manipulate it to solve for our force. So I know pressure equals force divided by area, and I know my pressure is going to be 5.1 times 10 to the fourth. My area is 8.4 times 10 to the negative third. And then I can solve that to get my force. So we have our 5.1 times 10 to the fourth equals force over 8.4 times 10 to the negative third power. And so to get my force, I just have to multiply by that denominator, and then we'll get our answer. So I get 5.1 times 10 to the fourth times 8.4 times 10 to the negative third is equal to my force. And this is 4.3 times 10 to the second power newtons. That is my force. So this problem was just a straight manipulation of the pressure equals force divided by area formula. Nice and straightforward. Now to start getting a little more complicated, we have to talk about the mass density and weight density of a fluid. So the definition, the mass density of a fluid is defined as delta equals m over v, where m is your mass and v equals the volume of your fluid. And for this particular video, we're only talking about homogeneous fluids, and that just means that the density is the same for the same volume of the same type of fluid. So it's all nice and uniform. That formula is our mass density, and the weight density is rho equals W over V, where W is weight and V is volume. And in pretty much all the problems that we're going to see in this class, they're going to tell us the weight density or mass density that we need. There are lots of different densities for different types of fluids, and you can always find those by Googling them if you needed to find something that was not given in a problem. All right, so what are we going to do with these densities? Well, let's suppose that a flat surface is going to be submerged in some fluid. So suppose a flat surface of area A is submerged horizontally at a depth of H in a fluid of weight density rho. Then the fluid exerts a force equals rho times that depth times the area on the surface and there is a pressure P, which is just rho H on that same surface. So now, if we're just talking about if we submerge our surface horizontally, that means it's laying flat like this in the water or whatever liquid it's being submerged in. If we do that, then there's a force given by the weight density times the depth times the area of our surface, and the pressure is just the weight density of the fluid times the depth. So let's do some examples calculating fluid pressure and force when we just have our surface submerged horizontally. So find the fluid pressure and force on the top of a flat circular plate of radius 2 meters that is submerged horizontally in water at a depth of 6 meters. And the weight density of water is 9,810 newtons per cubic meter. So we're just going to use those two formulas that we just had. We'll calculate the fluid pressure first. Your fluid pressure is going to be equal to the weight density times the depth where this is submerged. And then we're going to calculate the fluid force, which would be the weight density times the depth times the area of the surface. So we erase part part of our problem, so we still have all the info that we need. Let's start with the pressure. Pressure is equal to the weight density times that depth. My weight density is 9,810, and my depth was 6 meters. So all I have to do is multiply those together and get 58,860 pascals for my pressure. Now for my force, that formula is my rho times my H times my A. So that's my weight density times the depth times the area of my surface. Now my weight density is still 9,810 and the depth is still 6. And now we just need the area of the surface, which was circular and had a radius of 2. So the area of a circle with radius 2 would be pi times that radius squared, or 4 pi. So I have 9,810 times 6 times 4 pi, which is 235,440 pi newtons. And that's all there is to it for calculating our fluid pressure and force, at least when the plate is hanging horizontally. Now, if it's not down in the fluid horizontally, things get more complicated, and that's where the calculus actually comes in. So instead of having our surface horizontal like this in the fluid, we're going to talk about what happens when it's vertical in the fluid. That is when we're going to need our integrals. So suppose a flat surface is immersed vertically in a fluid of weight density rho, and that the submerged portion extends from x equals A to x equals B along an x-axis that is oriented downwards. Then for A less than or equal to x less than or equal to B, suppose that W of x is the width of the surface, and H of x is the depth of the point x. Then the fluid force, F, on the surface is, and then we get our formula for calculating this force. We get F equals an integral from A to B of rho, the weight density, times H of x, the depth at the particular point x, times Wx, the width of the surface at that point x, with respect to x. So if we're going to find the fluid force on the surface, we just need to find formulas for the width and for the depth of that particular surface, and we need to know the fluid density, the weight density. So let's do a couple of examples with that. Let's see. Here we go. This one's a good one. So an example. The face of a dam is a vertical rectangle of height 100 feet and width 200 feet. We want to find the total fluid force exerted on the face when the water surface is level with the top of the dam. And the weight density of water is 62.4 pounds per cubic foot. So I'm going to let you look at that for a second. We're going to draw a picture representing the face of this dam. So it being a vertical rectangle just means that we have the dam sitting vertically like this, and we have water coming against it. And we're trying to find that total force exerted by this water when the water meets all the way to the top of the dam. So let's go ahead and draw a picture of the face of this dam using all of the information that was given to us. So we have a rectangle, and we were told that it was 100 feet in height and 200 feet in width. And I'm going to introduce my x-axis with 0 up here at the top, 100 down here at the bottom, because we want our x-axis oriented downwards. So my a in this problem is 0, and my b is going to be 100. We want to have force equals an integral from a to b of our weight density times our depth times the width dx. So I just need to find a formula for h and a formula for w. So to do that, let's just pick an example. I'll say here's x. So looking at that little strip right there, what would be the width of the surface when we're looking just at the width at x? Well, luckily we have a rectangle, so the width doesn't change no matter where I'm looking at it. My width is still 200. It's important to still take a look because we're not always going to have a surface that is like this. Maybe it has a more triangular shape, so the width gets skinnier the higher up you go. All sorts of things can happen, so you should always double check. Now, what is the depth? Well, what is the depth of this particular point here? It's going to be whatever x is. If x is chosen all the way at the bottom, it's a depth of 100. If it's chosen way at the top, it's a depth of 0. So whatever we choose in between 0 and 100, the depth is equal to x. So now I can just take that information, plug it into my formula, with a is 0, b is 100, and my rho is that weight density, 62.4, that they gave us. So we get the fluid force is equal to an integral from 0 to 100 of 62.4 times my depth, which is x, times my width, which is 200, dx. And so I can take this 200 times my 62.4 and pull that outside of the integral. I get 12,480 times an integral from 0 to 100 of x dx. And now we're ready to just do an antiderivative. We know that we'll get a 1/2 x squared. So if I combine the 12,480 and the 1/2, I get 6,240 x squared, and we're evaluating at 100 and at 0. So we only need to plug in the 100, because when I plug in 0, I'm going to get 0. So I get 6,240 times 100 squared, which is 62,400,000 pounds of force. All right, so that one wasn't too bad. The hardest part of these, as always, is setting up the problem. Once you have your width, W of x, and your depth, H of x, it's just a matter of integration. So let's do one more example that's a little harder because we're not going to use a rectangle this time. So this time we have a plate in the form of an isosceles triangle. With base 10 feet and altitude 4 feet, is submerged vertically in machine oil. Find the fluid force F against the plate if the oil has weight density rho equals 30 pounds per cubic foot. And we're going to put a little note here, see picture. This problem comes with a picture showing the situation, which actually shows exactly how far down this particular plate is submerged in the fluid. So wait for the picture before you start trying to do the problem. So here is a picture of our situation. There's all my fluid, my machine oil. I have an isosceles triangle. Which has a base of 10 feet and it has a height or an altitude of 4 feet. The distance from the top of the oil to the top of the plate is going to be 3 feet. And this is the picture that would be provided for us on this problem. And now we want to find our force, which is an integral from A to B of the density times the depth times the width dx. So we need to find a depth and a width. Well, let's start with the depth. The depth is actually a little bit easier. For convenience, I'm going to choose my x-axis to start at the very, very top of my triangle. So I have 0 there, I have 4 here, and I'm looking on my interval from 0 to 4. Those will be my bounds of integration because that's the part that includes my surface. So I already know my A and my B and my rho. Let's find our H, the depth. Let me just choose some point X in my interval. And what is the depth of this point on my surface when I have X chosen between 0 and 4? Well, you might think it's X, but it's actually a little more because my entire triangular plate is submerged completely in this oil. In fact, there's 3 feet of oil above it. So the depth that takes me to X is actually 3 plus X, because I am already at a depth of 3 when I'm at my point 0, and I'm adding X more to that depth. So H of X is 3 plus X. Now W of X, I'm just going to put a question mark there right now because we actually have to do some geometry to find that. We can find W of X, the width. W of X is this distance here. We can find that width using similar triangles. So if I look at this isosceles triangle, the big one that we had, I also now have a little isosceles triangle whose base is W of X. So I can say W of X is related to 10. Those are the bases of my triangles. This should be equal to the ratio of the altitudes of the triangles. Well, I have an altitude of 4 for the big triangle and an altitude of just X for the little triangle, because it's the distance from just 0 to X. Now I can solve this to get that my W of X is equal to, multiply by 10, you get 5 over 2 times X, and that is my width of the surface at any point X. Now I have everything that I need. So plugging in the information, my force should be an integral from A to B of the density times the depth times the width dx. My bounds were from 0 to 4. The density that they gave us was 30. My depth was 3 plus x, and my width was 5 over 2 times x. And now we're all set up and ready to integrate. So I'm going to pull my constants out. I have a 30 times a 5 halves, and that would get me 75 outside of the integral. So 75 times the integral from 0 to 4 of 3x plus x squared, which I got by distributing my x to the 3 and the plus x. Now we're ready for our antiderivative. So I'm going to get 75 times 3 over 2x squared plus 1 over 3x to the third, evaluated at 4 and at 0. Now, when I plug in the 0, I'm just going to get 0. So I only need to plug in that 4. Plugging in 4, we get 75 times 3 over 2 times 4 squared plus 1 over 3 times 4 to the third. This is 75 times 24 plus 64 over 3, which is 75 times 136 over 3, which is 3,400 pounds for the force. All right, so that's actually all I have for you on fluid force and pressure. Shouldn't be too terrible. The problems involve a little bit of knowledge of how to set it up, but the integrals themselves end up being pretty straightforward. If you have any questions, feel free to drop them below, or if you're a current student, you can also ask in office hours or through email, and I will see you guys next time.